From our previous lesson, we have seen that we can increase the moment of a force about a point, that is the turning effect of a force about a point, by increasing the distance from the turning point to the line of action of the force. This is an important discovery because it enables us to increase the turning effect even when we use a small force. This is the reason the door handle is located as far as possible from the hinges. It is easier to open or close the door, that is, turn it about the hinges, when the handle is as far away from the hinge than when it is close to the hinges. This is leveraging distance to our advantage. When we make use of something to our advantage, we are leveraging that particular thing. In this case, we are making use of increased distance to overcome a bigger force elsewhere, hence the word leveraging. So let us list down a few applications of this aspect. So it is possible to increase the turning effect of a force by increasing the distance from the point to the line of action of the force. This enables us to overcome a bigger force elsewhere by use of a small force. The first application is in the spanner. It is easier to loosen a nut using a longer spanner than using one which is short in length. We have already seen this aspect. The door handle is usually located as far from the hinge as possible. And number 3, it is easier to turn a large steering wheel than one which is small. These are some of the applications of increased distance in order to increase the turning effect of a force. We have also seen that we can increase the turning effect of a force by using a larger force. This is alright if we are very strong. It also means that we get tired quickly. So this may not be a very good option. The first option is the best because it allows us to use a small force to overcome a bigger one, and thereby we don't get tired so easily. I hope you're beginning to see how these concepts can be used in our everyday life to make work easier, to make our lives comfortable. Now let us go ahead with calculations, where we are still calculating the turning effect of a force about a point, that is, moment of a force about a given point. Now over here, we have a system of forces. There are 7 forces. First force, the second one, all the way up to the 7th force. They have different magnitudes and they are at different distances from the point about which we want to take moments. In this particular lesson, we want to calculate the moment of each force about point O. Let's say this is the point that we are referring to, this one here, about point O. So let's start by calculating the moment due to F1 about that point. So we want to calculate the moment due to F1 about point O. So we identify where F1 is. This is F1 and this is its line of action. The distance from O, which makes 90 degrees with its line of action, is 2 meters. So we are going to say that moment due to F1 is F1 itself times the distance from O, which is, we can say it's D1, and this will give us 10 newtons times 2 meters, and we get 20 Newton meters. And you can see this moment, the moment of this force about this point, tend to turn this system clockwise about point O. So we write CW. As simple as that. Let's go to F2. F2 is here. Again, we want to calculate the moment of F2 about point O. So it will be equal to F2, which is 13 newtons, times D2, which is 2 meters, and this gives us 26 Newton meters in the anti-clockwise direction. You can see it tends to rotate this system about point O, like that, in that direction, about point O. Remember that the moment due to F1 was clockwise. Let's go to F3. What is the moment of F3 about point O? This is our point O. The distance from O all the way to the line of action of F3 again is this distance plus this distance plus this distance. That is 6 plus 4, that is 10 meters. So the force itself is 4 newtons times 10 meters. Again, here we get 40 Newton meters in the clockwise direction. Tends to turn the system about this point in the clockwise direction. F1 is turning the system about this point again in the clockwise direction. Notice that the two forces are on opposite sides of this point, but they turn the system in the same direction. This is something which I want you to note right from the start. Because when we come to the principle of moments, we'll be confronted with forces which are on opposite sides of the pivot, but they tend to turn the system in the same direction. It's important to be able to realize whether the moment is clockwise or anti-clockwise. Let's go to F4. Moment due to F4 about point O, this is our point O, is F4 itself, which is 6 newtons, times how far it is from point O, and this is 6 meters, and this gives us 36 Newton meters clockwise. So far we have F1, F3, and F4 turning the system in the clockwise direction. Let's go to F5. The magnitude of F5 is 10 newtons. The distance from O, which makes 90 degrees with its line of action, is 3 meters. And this gives us again 30 Newton meters in the clockwise direction. How about F6? The magnitude of F6 is 7 newtons. But the distance from point O to its line of action is 0. So the moment due to F6 about point O is 0. So it does not produce any moments about point O. This is very important. If a force happens to have its line of action passing through the point about which we are taking moments, then its moment about that point is 0. Again, this is the second important point that we must note. When we come to the principle of moments, we'll be confronted with situations whereby the moment due to some forces is 0, and we need to know how to handle them. Let's go to F7. The magnitude of F7 is 12 newtons. But its line of action happens to pass through the point about which we are taking moments. We are still taking moments about point O. So, you see that since its line of action passes through the point about which you are taking moments, then the distance from the point to its line of action is 0, and that makes its moment about that particular point to be 0. This is very, very important. Very, very important. So in all these situations, we were taking moment about point O. F1 tends to turn the system clockwise, and so is F3, F4, and F5. The only force which tends to turn the system in the anti-clockwise direction is the 13 Newton force, which is F2. The moment due to F6 and F7 about point O is 0 respectively. Each one of them has 0 moment about point O. And the main reason is because the line of action of that force passes through the point about which we are taking moments. When that happens, then the perpendicular distance from the point to its line of action is 0. And when we multiply any number by 0, you get 0. Very, very important. So always ask yourself, try to trace that line of action and see whether it passes through the turning point. If it passes through the turning point, then its moment about that particular point will be 0. So in any one system, we can have more than one moment, more than one clockwise moment, for example. Like we have already pointed out, we've got 4 of them tending to turn the system clockwise and 1 tending to turn the system in the anti-clockwise direction. And remember, we have not come to the principle of moments yet. So don't start using the principle of moments at this point. The only thing which I want us to practice on is to calculate the moment due to a given force about a given point. Now, how about if we change the point about which we are taking moments? What would happen? For instance, let's change the point about which we are taking moments to be, for example, this point here. Let this point be our turning point. We have changed the turning point from this point all the way to this point. Can you identify the force whose moment about point O is 0? And how did you do that? F4 is the force whose moment is 0 about this new point, because its line of action passes through point O, the turning point. How about the magnitude and direction of the moment due to the other forces? Let's look at the F1, the force F1. Its moment about this point was 20 Newton meters clockwise. How about if we change the point and we are taking moment about this other point here? The distance now changes from 2 to 8. So you'll find that the moment due to F1 about this point will be equal to F1 itself, which is 10 newtons, times 8 meters. And this will be 80 Newton meters clockwise. In the previous example, the moment due to F6 was 0. In this case, is it 0? I don't think so. So the moment due to F6 is going to be equal to the magnitude of F6 itself, which is 7 newtons, times how far it is from here, which is 6 meters, and this gives us 42 Newton meters in the anti-clockwise direction. So changing the point about which we are taking moments can have several effects. One of them is that the moment due to the forces change. Like you can see, the moment due to F1 has changed from 20 when the point was this one to 80 when this is the new turning point. The moment due to F6 has changed from 0 to 42 when this one was the turning point to this point here. Let's look at the moment due to F5. The moment due to F5 will be equal to the magnitude of F5, which is 10 newtons, times how far it is from the new turning point, which is 3 meters, and this gives us 30 Newton meters in the anti-clockwise direction. How much was the moment due to F5 previously? Its moment was 30 Newton meters anti-clockwise. Now it is 30 Newton meters in the anti-clockwise direction. Just by changing this point, by changing the point about which the system turns, you can change the direction of the moment due to any one force. Because previously, F5 was turning the system this way, which was clockwise. Now it's turning the system this way, which is anti-clockwise. However, the magnitude of F5 about this point and about this point is still the same because the distances involved are still the same, 3 meters and 3 meters. Let's look at the moment due to F3. The moment due to F3 is the magnitude of F3 itself, which is 4 newtons, times how far it is from point O, which is again 4 meters, and this becomes 16 Newton meters in the clockwise direction. So the direction due to F3 about this point is still clockwise. The moment due to the 13 Newton force also changes. It will be 13 newtons times a distance of 8 meters. So these examples are important. We've been able to see how we determine whether moment is clockwise or anti-clockwise. We have seen that when the line of action of a given force passes through the turning point, then its moment about that particular point becomes 0. We have also seen that in any system of forces, we can have more than one clockwise moment or more than one anti-clockwise moment. And we have seen that when we decide that we are going to take moment about a particular point, then all the distances for all the forces are measured from that particular point. Changing the point about which we take moments can have two effects. One, it can change the magnitude of the turning effect. That is, it can change the magnitude of the moment, or it can change the direction of that moment, or it can have both effects. This is very, very important. So these are some of the points which you need to bear in mind when you are looking at problem solving as far as calculating moment of a force about a point. Now, before you go to the next video, make sure that you've gone through some of the exercises that I've given you below so that you can have further practice on this particular aspect. It's very important that you practice how to calculate moment due to a given force about a particular point. The reason I'm doing this is because every time I give a question and asking students to calculate moment due to a given force about a point, immediately the first thing they write down is the principle of moments. They write down something like clockwise moments equals to anti-clockwise moments. But the question does not require you to use the principle of moments yet. The instructions are very clear. The instructions are calculate the moment of a given force about a given point. That is why I'm giving you all this practice so that you can be able to conceptualize this particular idea. Put it in your mind that there is a difference when you are asked to calculate moment due to a given force and when you are asked to use the principle of moments. So let's stop this video at this particular point, and I will see you in the next video where we will talk about another concept.